So congratulations, you have made it this far, that this is the end lecture we have regarding our course in solid state physics. And here I felt that it would be nice to also look into the properties of dielectric materials, essentially when we would be doping them intentionally and thinking of potential applications that we could have for these kind of dielectrics. So that this is of course something that I have a very I'm very fond of these kind of topics, since I'm optical physicist myself, and this is the approach how we can make laser gain materials. So maybe that also partly motivates and explains the final section. But on the other hand, I think this is also nice because it shows that in addition of doping semiconductors, we can also do the same thing for dielectrics. And hopefully you also understand that the electronic band structure is really being dictated by the kind of overall periodicity of the problem. And then if you have a slight impurities, some kind of additional atoms there, it doesn't really ruin the band structure as such yet, but rather the impurities, the dopants, can be described as individual elements. So hopefully this lecture we will look into the yttrium aluminum garnet. It's a dielectric host medium that we will be looking into, and we can show that we can make laser gain crystals by just intentional doping of this kind of crystal. And hopefully this lecture also clarifies to you that we can really quite easily combine different branches of physics in looking at these things. So what we are doing here, for example, is that we are combining the kind of basic concepts and notions from atomic or molecular physics, so that essentially to understand how these impurities behave, and then we have an application in mind, and that arises from photonics, so that we would be interested in understanding how a laser gain crystal behaves and how it could be engineered. And then, of course, on the background or in the foreground, we have the solid state physics. So how we can understand how a dielectric host medium works out and how we can dope that. So I hope this helps you to get a little bit better glimpse of the big picture, so that in physics, many times it's also good to kind of take a few steps back and try to see the kind of bigger scope of things. And to me, at least personally, I've learned a great deal by doing these kind of exercises and trying to broaden my scope. So instead of not focusing on some single thing, I rather try to look on the big picture. And this is especially true when we are looking at this solid state physics and condensed matter physics in general, that there's so many things that we can combine these topics with, that they will be very rich possibilities for us to kind of learn new things in the future, while we remember what we have covered so far and understand them, so that we can apply them into other branches of physics. So this is what we have in mind, and let me then, without further ado, continue with the actual lecture. So we want to connect these different concepts, different topics also already discussed in this course. So defects and impurities that we covered earlier, and also dielectrics that we are focusing here in this chapter 7. And I wanted to elucidate to you with this approach that there's a lot of connections, first of all, between the topics that we have covered in this course, and also a lot of connections with other branches of physics. And many times when we are thinking that we are looking at defects and impurities, we often may think that they only degrade the performance of the fabricated devices, that somehow defects and impurities, they only make things worse. But I want to highlight to you that this is of course not always true or the case when we are looking at things. So one a very, very clear example that clearly tells us that the impurities can also be improving things dramatically is that we could consider extrinsic semiconductors. And those, of course, where semiconductors will be intentionally doped the intrinsic semiconductor to make it extrinsic, and then we were able to dramatically change the electrical conductivity of the semiconductor. And even more importantly, by choosing different kind of dopants, so p doping or n doping, we were able to make p-n junctions, p-n-p junctions, so transistors, and basically the kind of modern semiconductor physics and semiconductor like industry relies on these capabilities. Another possibility that we can do when we add impurities, dopants into a dielectric host medium, not a semiconductor anymore, is, for example, laser gain crystals. And here, for historical reasons, let's just focus on a synthetic Garnet crystal. Incidentally, you can find Garnet crystals from Lapland, from many places. Like I've also found them myself with the family. So that they, like in Lemmenjoki National Park, you can find these Garnet crystals. So it's actually like you can even find these not artificial, but like natural from nature. It's a piece of a jewel. And the generic form, I'm not a chemist, but I read from Wikipedia that the generic form a Garnet crystal is that it's of a like X3, Y2, and zinc oxide for something, and this is, I guess, the synthetic. It's a generic formula for different kind of Garnets. And this is what we will be focusing on. The nice thing about Garnet crystals, and especially in yttrium aluminum Garnet crystal, is that it's transparent, and the chemical composition of yttrium aluminum garnet is like this. I do not try to pronounce this, but the chemist would be able to do that. And this is a pronunciation I can do, so I can use the abbreviation of a yttrium aluminum garnet, so it's often called just a YAG crystal. A YAG I can pronounce. Negligible YAG, yes, I can do this, but that this guy, I'm not embarrassing myself more of trying to pronounce that out. As with all Garnet structures, and this is a prime case of the structure dictates function notion, a YAG crystal also is a dielectric medium. And all of these formulas like that resemble a generic form, in essence they are dielectrics, so that they are quite transparent for visible radiation. And basically, so that they are dielectrics, they even in fact have quite large band gaps, so the EG values are of the order of 6 or 7 electron volts. For the case of YAG crystal, the band gap is 6.52 electron volts, and that corresponds to a case of roughly 100 nanometers of UV light when we start having a kind of like possibility that we are exciting a valence electron into the conduction band. So when we are shining visible light into a YAG crystal, it's really mostly transparent. It doesn't absorb that kind of light at all, and that's quite nice. And even in the case that the band gap is so large, we can even use a powerful visible light in order to excite a YAG crystal, and nothing much will happen because we would need a nonlinear process. 2 photons would need to be lifting a single electron state up in a process of multi-photon excitation in order to have a electron state be excited from the valence band to the conduction band. So what I'm trying to say is that the most of the time YAG crystal is really transparent to light, and you would really need to go quite intense excitation levels. So in essence, you would need to go from linear optics to nonlinear optics in order to see some absorption, 2 photon absorption or 3 photon absorption in a YAG crystal. So that's the nice thing of working with dielectrics. And the nice thing about YAG crystal is that we can make a laser gain crystal out of it by basically replacing some of the yttrium ions that we have with rare earth ions inside. And this, because we are only doping the YAG crystal slightly, so we're only replacing yttrium ions here and there, the lattice remains relatively untouched, and of course the kind of band structure remains, so it remains as a dielectric and mostly transparent to visible light. So we dope a YAG crystal with rare earth impurities, and the nice thing about them is that if we choose the rare earth impurities appropriately, we can then in a controllable manner excite these impurities, and then we can do physics with them. Historically, neodymium was the kind of dopant that has been used. So neodymium is trivalent, and this has been the most important one. And in this case, a YAG crystal has been turned into a neodymium doped aluminum garnet, so ND YAG laser gain medium. See, this is how the terminology goes. So when we dope a crystal, we add the dopant in this way into this. So neodymium YAG is essentially a YAG crystal doped with neodymium, and Ti sapphire is essentially a sapphire doped with titanium dopants and so forth. And other dopants, of course, can be used, particularly ytterbium YB has been recently used quite a bit. And the nice thing about it that the really high power lasers can be done that they operate at 1030 nanometers. So this is the kind of current state of the art in terms of high power laser development, and they are being used in many applications. The band gap, like we already mentioned, the EG value is quite high for YAG, so 6.52 electron volts. And this, of course, means that there's really no absorption of visible light taking place inside YAG. So this is nice. So we don't need to consider about the YAG crystal, the dielectric host medium much. The only thing that we must consider when we want to make a laser crystal is that what happens for these ND ions that are now present inside the doped ND YAG crystal. And they will give rise to defect states and bands that we can now excite using visible light. So this is what happens. And because they are not very, very concentrated, the kind of concentration of impurity atoms, so these ND ions, is not very high. So mostly they retain their individuality inside the host dielectric, so that we can really have a look on molecular physics and atomic physics, and we can see how a ND atom would behave. And this is essentially a kind of energy diagram that is associated with the ND3 ion, that what kind of states we have. And this is the nice thing, that we can really have this kind of a quite controlled atomic energy level system inside our passive dielectric host medium. And then when we shine light into it, we know that essentially only these ND ions will respond, and we know how they will respond because they don't really couple with each other. And what we can do when we have formed this kind of ND YAG crystal is that now we can move electron states from the ground state. So that will be our I9/2 4 state here. So this is our ground state. And we can move an electron from here by shining light into this excited state F5/2 4. And this is now the kind of energy difference between these corresponds to 1.53 electron volts. So if we shine a photon that has a wavelength of roughly 808 nanometers, we can make this transition to take place. And when it takes place, the F345/2 state relaxes quickly, and it doesn't radiate. So it just relaxes via phononic relaxations and thermal relaxations into a long-living F3/2 state. So we excite system with light, we pump electrons into this state, they non-radiatively decay here in nanoseconds, and this state is actually quite long-lived. So inside the parentheses, there's the approximate lifetime, so 230 microseconds of this state. And then this is nice because if we control then what is the lifetime of this state, we may be able to make a population inversion between these two states. And this is what we do. And with neodymium, we were lucky, so that this I11/2 state is actually also a state that decays quite quickly. And then this ensures that we can actually easily achieve population inversion between the states of F3/2 and I11/2. So essentially, we can ensure that we can pump electrons effectively easily into here, they decay into here, and because this state this F3/2 is long living, then the electrons remain here for a long time. And then if this is not a long living state, when they relax, they quickly also relax to the ground state. And essentially we form a 4-level laser system. And then we can easily create a population inversion between these two states. And this ensures that we can actually quite easily make a laser gain crystal out of the system. So this is what I wanted to say. And at least when I started teaching this course and solid state physics, I really enjoyed adding these final parts into the curriculum of this course, because it really shows also that when we have a solid state system, this YAG crystal, a dielectric host medium, by just adding impurities there, like we can now understand, as long as the concentration of impurities is not very large, we can also just understand their properties from atomic physics and molecular physics point of view. And then it's actually, we can nicely like engineer the system and its response. And in that, and these considerations were not clear to me, that what happens, that how exactly you can make an ND YAG crystal and how it behaves. Like it wasn't exactly clear to me before I started teaching this course. So I'm kind of hopeful that you also appreciate now a little bit better of these kind of possibilities that are in our disposal to understand now that we have taken this kind of course. And this is the final lecture, and this is the final slide, and this is the final sentences I'm saying to you. I'm thankful that you have had the patience to listen my monologues during these hours. I really hope that you have enjoyed the course, and I hope that you have learned new things. And I wish you a very good day, even the good rest of the week. And I hope you will join my courses in the future, and you will have equally fun time in kind of learning new things. At least I've had pleasure in teaching you, and I hope that we will see sometime soon in the future during other courses. So I thank your time, I thank your patience, and I thank your diligence regarding learning the things that we cover in this very introduction course on solid state physics. Good stuff has been on the way, but for sure good stuff will be on the way also in the future. So thanks and bye-bye.